Today we're going to do section 4-6 rank. Row space, the set of all linear combinations of the row vectors of a matrix A is called the row space of A and is denoted by row A. Let A be that matrix and R1, R2, and R3 be the rows. Row A span R1, R2, and R3, a subspace of R4. Theorem 13. If two matrices A and B are row equivalent, then their row spaces are the same. If B is in echelon form, the non-zero rows of B form a basis for the row space of A as well as B. So let's look at example 1. The matrices A and B are row equivalent. Find a basis for row space, column space, and null space of A. Also state the dimensions of each. So we know, since these are row equivalent, my pivot columns are column 1 and column 2. Therefore, that gives me the dimension of column A, which also gives me the basis of column A. So my basis for column A would be row 1 of A, which is -1, 2, 1, and row 2 of A, which is 2, -5, -3. And the dimension of column A is 2 because of the number of pivot columns. Now the basis for row A is the first row and the second row by theorem 13. The dimension of row A is also 2. So now I need to find the basis of null space of A. So therefore, I need to take matrix B and get B in echelon form. So when I do that, I would have this matrix here. And x1 would equal -3x3, -6x4. x2 would equal 0. x3 and x4 would both be free. So I would have x1, x2, x3, x4 equaling x3 times -3, 0, 1, 0, plus x4 times -6, 0, 0, 1. And the basis for null A would be V1 and V2 if I called those V1 and V2. So I'm going to write that right over here. And the dimension of null A would be 2. Rank. The rank of A is the dimension of the column space of A. Rank A equals the dimension of column A. The number of pivot columns in A equals the dimension of row A. So rank A is the number of pivot columns plus the dimension of null A, the number of non-pivot columns of A, equals n, the number of columns of A. Theorem 14, the rank theorem. The dimensions of the column space and row space of an m by n matrix A are equal. The common dimension of the rank of A also equals the number of pivot positions in A and satisfies the equation rank A plus dimension of null A equals n. Since row A equals the column of A transpose, the rank of A equals the rank of A transpose. So let's go ahead and look at example 2. Suppose that a 5 by 8 matrix A has rank 5. Find the dimension of null A, the dimension of row A, and the rank of A transpose. Is column A equal to R5? So this is my m by n matrix. And since I have rank 5, that's my number of pivot columns. So let's start with the dimension of null A. The dimension of null A is columns minus rank. And I have my columns, which would be n right here. And I have my rank, which we would get by right here, which is 5. So this would be 8 minus 5, which equals 3. The dimension of row A equals 5 because it is equal to the rank of A. The rank of A transpose equals 5 because it's equal to the rank of A. And yes, column A is an R5 or equals R5 because there are 5 pivot columns. So there's a pivot in every row. Let's look at example 3. For a 9 by 12 matrix A, find the smallest possible value of the dimension of null A. So we need to go back to our formula, rank A plus the dimension of null A equals n. Well, we know n is 12. So we'd have rank A plus the dimension of null A equals 12. Well, the maximum value that rank A can be is 9, because that's the number of pivot columns, the max number of pivot columns that our matrix could have, since it has 9 columns. So 9 plus the dimension of null A equals 12. Subtract 9 from both sides, and you get null A equals 3. So the smallest possible value of the dimension of null A would be 3. Let's look at visualizing row A and null A. Example 4, we have this matrix A equal 1, 0, negative 1, and 2, 0, 2. One can easily verify the following. The basis for null A. So the basis for null A would equal 0, 1, 0, 1, 0, 1. And therefore, null A is a plane in R3. The basis for row A is 101. And therefore, row A is a line in R3. So if I want to visualize this, these are the subspaces null A and row A. The basis for column A would be 1, 2. And therefore, column A is a line in R2. The basis for null A transpose is negative 2, 1. And therefore, null A transpose is a line in R2. So this is the subspaces null A transpose and column A. The rank theorem provides us with a powerful tool for determining information about systems. Let's look at example 5. A scientist solves a homogeneous system of 50 equations in 54 variables and finds that exactly 4 of the unknowns are free variables. Can the scientist be certain that any associated non-homogeneous system with the same coefficients has a solution? So take a minute and think about that. And your answer should be yes. If we let A be the 50 by 54 coefficient matrix of the system, the given information implies that 4 solutions are linearly independent. And span null A. So the dimension of null A equals 4. And by the rank theorem, the dimension of column A is 54 minus 4. Which is 50. Since R50 is the only subspace of R50, whose dimension is 50, column A must be all of R50. Therefore, every non-homogeneous equation, AX equals B, has a solution. The invertible matrix theorem continued from section 2.3. Let A be a square n by m matrix. The following statements are equivalent. M, the columns of A form a basis for Rn. Column A equals Rn. The dimension of column A is n. Rank A equals n. Null A is the zero vector, and the dimension of null A is 0.